Hello everyone, I hope you're doing well. So in this video, I'd like to talk a little bit about linear approximation and differentials. So here, the key idea is how we can approximate values of our function by simpler things instead that we can actually compute. And this has various applications, for instance, in solving equations, or even you could ask, philosophically, if you have a function like e to the x, and if you wanted to compute, say, e to the power of 3 or e to the power of 4 or whatever, how would you actually compute that without a calculator or a computer? Or even if you do have a calculator or a computer, how does a calculator or computer actually compute these things? Okay, so let's get started. So here is the question we just said. So how do we approximate a function f of x by something simpler that we can actually compute? And the idea is that if we're close to a number x equals a, the graph of a function y equals f of x is well approximated by the graph of the tangent line, right? Remember, at a, if we take the tangent line is the line that passes through the curve at a and has the same slope. So at the point, if you zoom in, they're pretty close together. So the tangent line, we normally write it as y minus y1 equals m x minus x1, and the point is a comma f of a, the slope is f prime of a. So you can rearrange the slope of the tangent line to have this formula. Okay, so since the graph of the curve is well approximated by the graph of the tangent line, that means also the y values are going to be pretty close. So the y value of the curve is going to be close to the y value of the tangent line, at least if we're close to a. So if we put that together, we get f of x is close to f of a plus f prime of a times x minus a. Okay, and this is the approximation we have in mind that's called the so-called linear approximation or tangent line approximation. So we say f of x approximately equal to f of a plus f prime of a x minus a. For x close to a, it's called the linear approximation or the tangent line approximation of f at a. And all we're doing, we said, is we're setting the y value of the curve, which is f of x, is approximately equal to the y value of the tangent line, which is this thing on the right. And this is a good approximation if x is close to a. If x is far from a, it's often not such a good approximation. It doesn't quite make sense, remember, because then if you move far from a, the tangent line and the curve can diverge very strongly. In that case, you would have to do something like Taylor series with more terms, but you will learn about that if you do calculus 2. Okay, but for now, this is going to be a great approximation for x close to a. And the thing on the right is important. It has a name. It's called the linearization of f at a. So we just took this thing on the right-hand side and we called this L of x. This is the linearization. And this is a linear function. So all linear function means is it looks like constant times x plus constant. So anything that looks like that is linear. And right now, this might seem kind of special, but if you ever go on to do, differentiated functions of multiple variables and what it means to differentiate in that context, differentiability will just mean that the function is approximated by a linear function in a very special way. So here is your first introduction to linear functions. Okay, so let's do some examples. So let's first find the linearization of f of x equals sine x at a equal pi over 6. So all we have to do is use the definition of linearization, right? We're told what is f, we're told what is a. We just have to compute the unknowns and substitute them to get our linearization. So the linearization is supposed to be f of a plus f prime of a times x minus a. So we have to compute f of a. So we have sine pi over 6, that's going to be a half. And then we have to compute f prime of pi over 6. So if f of x is sine x, f prime of x is cosine x, we sub in pi over 6, we get f prime of a is cosine pi over 6, which is root 3 over 2. So we have our unknowns and we just plug them into our formula. So f of a plus f prime of a times x minus a, that's going to give us a half plus square root 3 over 2, x minus pi over 6. So, as long as you remember the definition of linearization, any problem like this is pretty simple, pretty straightforward. You just compute the unknowns and sum them. Okay, so let's go on to a problem that involves actually doing approximations. So how is this helpful? So let's try to use a linear approximation to approximate the value of e to the power of 0.1. So in this case, they didn't tell us the point a to take the approximation, and they didn't tell us the function f of x. So we have to come up with those. And we should make choices so that f of a and f prime of a are easy to compute. So if we look at the advantage of the approximation, f of x is approximately f of a plus f prime of a x minus a. On the left, we have a very complicated function f of x. Depending on the value of x, it might be easy to compute, it might not be easy to compute. But on the right side, to actually compute the right side for any value of x, all we need is f at a specific point, f prime at a specific point, and then we need to be able to multiply things and add them together. So the right side is much easier to compute. Okay, so we want to pick a function f. Well, let's choose e to the x. Seems like a pretty close function to e to the 0.1. And then we have to choose a. And remember that we have to be able to compute f of a and f prime of a. So choosing a equals 0.1 would not help us because then in order to compute the approximation, we would have to compute f of a, which would be e to the 0.1, and that's our entire problem. So we shouldn't choose a equals 0.1, but instead we should choose a to be a nearby point. So it has to be nearby for the approximation to make sense. So a should be a nearby point so that we can actually compute f of a and f prime of a. Okay, and the only easy place that I know, or one of the places that I know to compute e to the x is going to be at 0, right? We know how to compute e to the 0, and we know how to compute the derivative at 0. So let's choose a equals 0. Okay, we compute the linearization. So f of x is e to the x. If we sub in 0, we get e to the 0, which is 1. F prime of x is just e to the x. So again, f prime of 0 is 1. Now we can use our approximation formula. So e to the x, which is our function f of x, is approximately f of a, which is 1, plus f prime of a, which is 1, times x minus a, so x minus 0. And then if we clean that up, it's just 1 plus x, right? And this is valid for x close to a, which in this case is x close to 0. So now we have this beautiful approximation that says e to the x is roughly 1 plus x for x close to 0. So what were we actually doing? We were trying to compute e to the power of 0.1. So we want to take this approximation and we sub in x equals 0.1. We're going to get e to the power of 0.1 is roughly 1 plus 0.1. Okay, which we can actually do, right? That's 1.1. Okay, so this is our approximation. E to the 0.1 is roughly 1.1. And notice there were several steps, right? So we had to choose our function, and we had to choose a, and we had to choose it in a careful way so that a is close to the value we're trying to actually compute or approximate. But f of a and f prime of a have to be something we can easily calculate. So in this case, it made sense to choose 0, right? That was the only thing that we could easily calculate f of a and f prime of a for. Okay, so let's do another example. And here we're actually told what is our function f and what is a. So first find the linearization of square root of x at a equals 4 and use it to approximate square root of 4.1 without a calculator. So what do we have to do? Remember the definition of linearization, right? It's f of a plus f prime of a times x minus a. So we have to compute f of a and f prime of a in this case. So f of 4 is square root of 4, which is 2. F prime of x, f is x to the half. So we get a half x to the minus a half when we differentiate. So f prime is 1 over 2 square root x. If we sub in x equals 4, we get f prime of 4 equals 1 over 4. Right, we get 1 over 2 times 2, so 1 over 4. So these are our unknowns, so now we can write out the linearization. Right, by definition, it's f of 4 plus f prime of 4, x minus 4. We sub in our 2 and our 1 over 4, we get 2 plus a quarter x minus 4. So this is the first part. We found the linearization of the square root function at a equals 4. And now in the next step, we want to use it to approximate square root of 4.1. So if we remember back to what was the point of this, the linearization was the right side in the approximation for f of x. So we're saying f of x is roughly equal to the linearization, they're close, if we're close to a, which in this case is 4. Okay. So since 4.1 is pretty close to 4, we can approximate f by the linearization at 4.1. Okay, so we approximate square root x by our linearization for x close to 4, as we just said. And now we want to approximate the square root of 4.1. So we're going to sub in 4.1, which is allowed because 4.1 is pretty close to 4. So we just sub in on our approximation 4.1, we get 2, and then we get a quarter, and then we have 4.1 minus 4, which is 0.1. And then we have to try to evaluate this. Okay, this one we can actually do if we work a little bit, right? 0.1 divided by 4 is 0.025, right? 1 divided by 4 is 0.25. You shift it along. 0.1 divided by 4 is 0.025. Okay, and then we can actually add these. We get 2.025. So this linearization approximation tells us that the square root of 4.1 is roughly 2.025. And just for comparison, it's not a part of this problem, but in reality, square root of 4.1, if you plug it in your calculator, you'll get 2.02484. Okay, so this is a pretty good approximation. And as for where this comes from, well, for instance, you could use Taylor series or Maclaurin series or something like that from and program it from Calculus 2, or I don't know how your calculator computes these things, but there are math ways that you could refine this calculation and get better estimates. And remember, the square root of 4.1 is probably going to be an irrational number, right? So this will have an infinite decimal. So this, even what you get from your calculator is an approximation if it's irrational. Okay, so final thing to wrap it up is differentials. So we're going to cover this lightly. It's not really a topic that we tend to test very heavily, but it is in the course, so let's talk about it. So suppose we have a differentiable function y equals f of x, then we define two differentials. So the first differential dx is an independent variable, so it's just an input that we're going to use to do something else in a second. So that's all it is. Dx is something we input. Like x, in an equation, we have something involving x, we plug in a value of x, we get something out of it. Dx is something we're going to plug in. And then dy is the differential dy is an output. So it's a dependent variable, and it depends on both the value of x and dx. So if I give you an x and a dx, which could be different values, you can compute dy according to this formula, just multiply them. Just multiply f prime of x by dx. Okay, so if I give you x, I give you dx, you compute f prime of x, it's a number. I give you dx, which is a number. You multiply them, you get dy, which is another number, which is your output. Okay, so dx is just an input, dy is an output. So for instance, here is a simple example. Let's suppose we have y equals x squared, so our function is x squared. Find the differential dy and evaluate dy when x equals 1 and dx equals 0.1. So notice there are two inputs, right? There is the x and there is the dx. Okay, so if we want to find dy, we just have to use this formula, f prime of x times dx. That's the definition, right? If you don't know what to do, you always have to go back to the definition. So our function is x squared, we differentiate, we get 2x. So dy is equal to 2x dx. And then finally, we want to evaluate that when x equals 1 and dx equals 0.1. Okay, we can just sub those in, right? We get 2 times 1 times 0.1, so we get 0.2. So dy equals 0.2. So there's really not very much to it, right? Dx is an input, dy is an output. It depends on x and dx, and you compute it with this formula. Okay, so what is the interpretation of this? So remember that the tangent line to a curve at A has this equation, y minus f of a equals f prime of a x minus a, right? The point y minus y1 equals mx minus x1. The point is a comma f of a, the slope is f prime of a. So this is our tangent line. So if we think about the differential dy at a, which is f prime of a times dx, this is the right-hand side if we move from a to a plus dx, right? So if I sub in x equals a plus dx, I'm going to get f prime of a times dx. So the differential dy is the change in height of the tangent line when we move to a nearby point. And in contrast, this thing that people call delta y, which is equal to f of x minus f of a, this is the change in the height of the curve, right? I have the height of the curve at one point, the height of the curve at another point, I subtract them. This is the change in height of the curve. Okay, and all we need to know is that delta y is approximately equal to dy. So all we're saying here is that the change in height of the curve is roughly equal to the change in height of the tangent line, because the tangent line and the curve are close near to A. So dy is just an approximation for this thing called delta y, which is easier to compute in some settings. Okay, so that's it for this time. So remember the linearization and the tangent line approximation equations. The linearization is just the right-hand side of the tangent line approximation. And then there were those differentials dx, dy. Dx was an input, dy was an output. And remember that when we actually compute things with these approximations, say when we were computing e to the 0.1 or the square root of 4.1, we want to choose a nearby point so that we can actually compute f of a and f prime of a, and then we can sub in the value of x where we're trying to compute the function. So we don't want to compute the linearization or the approximation at the actual thing we're trying to evaluate. We need to find something that's easier to compute. Okay, that's it for this time. Take care, everyone. See you next time.